we can approximate the area under f of x equals x with x between 1 and 3 and above the x-axis with rectangles of heights at sample points xi star on intervals. Reds underestimate the area, blues overestimate the area. But these approximations get better and closer with more and thinner rectangles. In other words, we get the area with a limit of Riemann sums. Riemann sums give the approximate area of f of x equals x from a equals 1 to b equals 3. For us, we'll use two rectangles, and so delta x equals b minus a over n equals 3 minus 1 over 2 equals 1. Note that the left or right Riemann sums gives the values on the left or right of the interval. Note that if f is increasing, then left is less than actual area less than right. Similarly, if f is decreasing, then right is less than actual area is less than left. The limit of right Riemann sums will give the area of f of x equals x from 1 to 3. Here is the formula. Here are the specifics. Although we won't do it, the left Riemann sums, Ln, needs k minus 1 rather than k. Either way, the area comes from the limits. A equals limit as n approaches infinity Rn equals limit as n goes to infinity Ln. Note that b will depend on the largest sample. In this case, since k goes to n, we have a plus k delta x equals a plus n delta x equals b. These calculations show that the limit of the series becomes 4. Although we won't do them, there are midpoint sums and trapezoidal sums. If f is concave up, then midpoint is less than actual area less than trapezoid. If f is concave down, then trapezoid is less than area less than midpoint. Here is the definite integral of f from a to b. If the limit exists, then f is integrable on a to b. The symbol is called an integral sign. The f of x is called the integrand. The a is the lower limit of integration, and b is the upper limit. The symbol dx indicates that we are integrating with respect to x. The procedure of calculating an integral is called integration. Our original example now becomes integral from 1 to 3 x dx equals 4. The definite integral is a number. It doesn't depend on the variable of integration. When going left to right, areas above the x-axis are considered positive, areas below the x-axis are considered negative. The definite integral is the net area of the function above the x-axis. Constant, sum and difference, constant multiple, additivity, zero width, reversibility. Direction of the integral, to the right and to the left. Inequality, max and min, average, mean value. One can think of the average value as the height of the rectangle that has the same area and base as the function. Even function, odd function. The fundamental theorem of calculus 1. If f is continuous on closed interval ab, then with a less than equal to x less than equal to b, g of x equals integral from a to x f of t dt, g prime of x equals f of x, is continuous on closed interval ab and differentiable on open interval ab, and g prime of x equals f of x. The derivative of the accumulation, area so far, function g of x is f of x. The following slide just gives the idea. It is not formal at all. Starting with the function f, the accumulation function g of x equals integral from a to x f of t dt gives the area under the graph from a to x. Starting at a, we find the area up to x, and then up to x plus h. The difference in areas as h approaches 0 is approximately a rectangle with base h and height f of x. As h approaches 0 is approximately rectangular area, divide by h, and limit. What is the derivative of g of x equals integral from 0 to x e to the t squared dt? Here, f of t equals e to the t squared. Recall that g prime of x equals f of x, so g prime of x equals e to the x squared. What is the derivative of g of x equals integral 0 to x squared e to the t squared dt? Like before, f of t equals e to the t squared. Unlike before, here we have g of u where u equals x squared. To differentiate this composite function, we'd need chain rule. G of x equals g of u of x equals integral 0 to u e to the t squared dt. G prime of x equals g prime of u of x, u prime of x, equals f of u of x, u prime of x, equals e to the u squared times 2x equals 2x e to the x to the 4. What is the derivative of g of x equals integral x to x squared e to the t squared dt? Unlike before, we have x in both limits of integration and not just the upper. We need to split the integral and use reversibility. What is the derivative of g of x equals integral x squared to x cubed e to the t squared dt? Like before, we have to split the integral and use reversibility. The fundamental theorem of calculus 2. If f is continuous on closed interval ab, then integral from a to b f of x dx equals big F of b minus big F of a, where big F is any antiderivative of little f, that is, where big F prime equals f. The most general antiderivative of little f is big F plus c, constant, since a constant differentiated becomes 0. Note that the integral of a rate of change is the net change. Now we can relate the accumulation function and the antiderivative. G of x equals integral from a to x f of t dt. G prime of x equals f of x. G of x plus c equals big F of x. From this, on the next slide, we'll see that this due to changes in the accumulation function. Here are the details. Note that plus c's cancel out in definite integrals. Big F of b minus big F of a equals g of b plus c minus g of a plus c equals g of b minus g of a, which equals this from definition of g of x, equals integral a to b f of t dt. Fundamental Theorem of Calculus 1 and 2. If f is continuous on closed interval ab, then we have g of x equals integral a to x f of t dt, g prime of x equals f of x, and where big F prime equals f, then integral from a to b f of x dx equals big F of b minus big F of a. Basically, integration and differentiation are inverse processes. Compiling all the terms, using f of x equals x as our example, the antiderivative of little f is big F, where big F prime equals little f. Big F of x equals x squared over 2, as well as x squared over 2 plus 1, x squared over 2 minus 1, and so on. The indefinite integral of little f is a set of functions whose derivative is little f. Integral x dx equals x squared over 2 plus c, where we have antiderivatives for each value c. The accumulation function gives the area of little f from a fixed a to a variable x. G of x equals integral a to x f of t dt. The definite integral is a number that represents the net area. Integral 1 to 3 x dx equals 4. For definite integrals, we find the simplest antiderivative with c equals 0 and take out any constant multiple. Evaluate at the upper limit of integration minus the lower limit of integration. Calculation nuances. For f of x equals 1 over x, the most general antiderivative is not ln x plus c, nor ln absolute value x plus c. Rather, it is big F of x equals this, to account for the different branches of 1 over x. For us, we'll use ln absolute value x plus c, and then see if the absolute value is necessary. We'll revisit this nuance when we do differential equations. If there is a jump discontinuity, we could still find the integral by splitting up the interval. A point discontinuity does not affect the overall integral. Note that integral dx equals integral 1 dx. For applications, Integral from start to end of the rate dx equals quantity from start to end equals quantity at the end minus quantity at the start. Becomes this. In words, we add our starting amount with the accumulation of small changes, which equals the overall net change, so that we get the ending amount. For these examples, we should ask two questions. Is the function continuous on the interval? What sign do we expect? A positive, negative, or zero? A template for the calculations could be the following. Integral from x equals 1 to x equals 4 of negative x plus 3 dx. We get 3 over 2. Integral from x equals 1 to x equals 4 of negative x plus 2 dx. And we get minus 3 over 2. Integral from x equals 1 to x equals 3 of minus x plus 2 dx. We should get 0. Integral from x equals 1 to x equals 2, 1 over x dx. We should get ln 2. Note that the antiderivative of 1 over x is ln absolute value x, and it becomes ln x when the x value is positive. Integral x equals minus 2 to x equals minus 1, 1 over x dx. We get minus ln 2. Note that the antiderivative of 1 over x is ln absolute value x, and it remains ln absolute value x when the x value is negative. Integral x equals minus 1 to x equals 2, 1 over x squared dx. It is not continuous on the interval, and we expect positive. We get minus 3 over 2. Since the integrand is not continuous on the interval, none of the computations are valid. Integral x equals 0 to x equals 1, 2x squared dx should get 2 over 3. Integral of x equals 1 to x equals 2 of x plus 1 squared all over x squared dx. It's continuous on the interval, and so we have the following, and we get 2 ln 2 plus 3 over 2. Find the indefinite integral of this. We get cosecant theta plus secant theta plus c. If we had information like f of pi over 4 equals 2 root 2, then we could solve for c equals 0. If f double prime of x equals 6x, and f prime of 0 equals 2, and f of 0 equals 1, then what is f of x? We have the following. Now we can solve for c. We have the following. Now we can solve for d. F of x equals x cubed plus 2x plus 1. If f equals t cubed x to the power 4, to find this, we treat only box as a variable and everything else as a constant. And we have the following. After integrating, we can differentiate with respect to the variable and get our original function. To find this, we treat only box as a variable and everything else as a constant. And we get the following.